So last time we spoke about the resistors in parallel and resistors in series, and we said opposite to capacitors, resistors they add when they are in series, and when they are in parallel, 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3 and so on. And we said series I, resistance in series, they have the same current. Para V, resistance in parallel, they have the same voltage. Okay, and we started doing some conceptual questions, and let's move to a real question now. Okay, so like we did equivalent capacitances, we have to do equivalent resistances. Okay, but this is much easier now. 4 resistors are connected as shown in the figure. Find the equivalent resistance between A and C. So this is A here. This is A and this is C. Okay, so clearly I can already identify that these 2 resistances are connected in series, and these 2 resistances, they are connected in parallel. Okay, so I can combine them. I can combine these 2 resistances. Let's call this R1, R2, R3, and R4. Okay, so I can determine R1 and R2. This is equal to what? 12. So 8 plus 4. This is 8 plus 4. It's 12 ohms. Okay, and I can combine R3 and R4, and let me call it R3, 4. Okay, so since they are in parallel, the product divided by the sum is the equivalent resistance. 3 times 6, 18. 18 divided by the sum, which is 9, so that will give me 2 ohms. So this is what I have done. I did 6 times 3 divided by 6 plus 3, so this is 2 ohms. Okay, so now these 2 resistances are connected in series, so I can combine them, and I can get R equivalent is equal R12 plus R34. So R equivalent in this case is just equal to 12 plus 2, 14 ohms. Okay, so this is the equivalent resistance. The next question, what is the current in each resistor? Okay, so here, like the capacitors, I can work backwards. Okay, all right, so they gave us the potential difference, delta V is 42 volts. So delta V 42 volts. I can determine the current I, which is the same as the current here, I is delta V divided by R equivalent. Delta V is what? 42 volts divided by 14 ohms. That's 3 amps. So now I have the current I that's flowing through all of these resistances, but I have to be careful. Okay, so now the current I, so through R1 and R2 the current is I. So I1 and equal to I2 is equal to I is equal to 3 amps. But the current then splits into 2 currents. Let me not use I1 and I2, because I1 and I2 are this one and this two. Okay, so let me call it IR1 and IR2. Okay, so in order to determine the current through resistor R3, I can start by first of all determining the voltage between B and C. So this is here B and C. Okay, since I have the current, okay, and I have the resistance R34, which is 2 ohms, I can determine VB minus VC is equal to the current I times R34. R34 we already determined, that's 2 ohms. 2 ohms times 3 amps, that's 6 volts. Correct? Yes. Okay, so now I have this voltage. I can determine I1 and I2 because I use Ohm's law. I1 is equal VB minus VC divided by R1 divided by R3, sorry. Okay, so this is 6 divided by 6, that's 1 amp, 1.0 amp. Okay, and I can do the same thing for I2. I2 is VB, Ohm's law, VB minus VC. This is the voltage here, this voltage difference here, divided by the resistance, which I called R4. So this is 6 divided by 3. This will give me 2.0 amps. Notice I1 and I2, when you add them, they will give you 3 amps, which is equal to I. So the current going in, I, which is 3 amps, splits into 2 currents. One is 2 amps, and one is 1 amp, and one is 2 amps. Okay? So this is how we do equivalent resistances. So first of all, start by identifying which 2 resistors are connected in series, which are parallel and combined. Then you go to the next step. Okay, do not skip steps. Okay. So we have done this. Okay, so now we want to calculate the power. The power is not difficult because we already have the currents and the resistances. We can determine P1 is, we can use so this is, we call it R1. Oh, this is a different problem. Is it the same problem? Resistance. Okay, yeah, this is a different problem. Yeah, different problem here. Okay, so here we have 3 resistors are connected as shown in the figure. Okay, so we have 3 ohm, 6 ohms, and 9 ohm resistor. A potential difference of 18 volts is maintained between point A and B. So this is the EMF here is 18 volts between point A and B. Calculate the equivalent resistance of the circuit. So here you can clearly see that these 3 resistors are connected in what? Series or parallel? Parallel, because every 2 resistors are connected on both sides. So the parallel combination, we can write 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. Okay, so that's 1 over 3 plus 1 over 6 plus 1 over 9. So the common denominator can be 18. So 3 times 6 will give us 18. So we have 6 divided by 18 plus, we can multiply it by 3. So 3 divided by 18 plus 2, we multiply by 2. 2 divided by 18. So this is will give us 11/18. So R equivalent is 18 divided by 11 ohms. Okay, then find the current in each resistor. Okay, so since we have the voltage and para V, all of these resistances, they have the same potential difference, same voltage difference. So we can determine the current. So I1 is just equal delta V, which is 18 volts, divided by R1. Delta V is 18 and R1 is 3 ohms, so this is 6 amps. I2, same thing, delta V divided by R2, and so that's 18 divided by 6, that's 3 amps. And I3 is delta V, which is 18 divided by R3, which is 9, so 18 divided by 9, that's 2 amps. Okay, now I can calculate the power. I can use one of 3 equations. For power in a resistor, you can use either delta V times I, or we can use Ri squared, or we can use delta V squared over R. So here, since I have the current, or I have the voltage also, and the resistance, in fact, it's safer to use something that you are given, delta V squared over R1. No? So this is 18 squared divided by 3. P2 is delta V squared divided by R2. So this is 18 squared divided by 6. And P3 is delta V squared divided by R3, which is 18 squared divided by 9. You get the power. Okay? So you see resistance circuits are easier or simpler than capacitive circuits. So these are the values that we find in this problem. Okay, for this question, I'd like to start the Kahoot. Okay, so please join this Kahoot here. Okay, and okay, now. Okay, so please load the pin. This 11489, 11489. Okay, let's start. Okay, so here you have light bulbs in figure are identical. Assume they have the same resistance, these light bulbs, and let's assume that it's fixed resistance. Which configuration produces more light? Okay, and so you have A, B, and C. Series connection produces more light. Parallel connection produces more light. Series and parallel connection produce the same light. This requires some thinking. So I'll give you a minute, and you can discuss it with your neighbor. So think, pair, and compare. Think, pair, and compare. So obviously the batteries are the same. Delta V is the same. Resistances are the same. R and R, R and R. Which one will produce more light? This is one of the questions you cannot just reason about it. You have to write things down. Assume the same resistance, same potential, delta V, the battery gives the same voltage. Which one gives more or brighter light? Ready? Huh? Anybody ready يا جماعة؟ ولا not? If you're ready, raise your hand. Oh, okay. The majority are ready. Okay, we can start, huh? Okay, 10 seconds only. Aha, very good. 25 are correct. And this is not a simple question, by the way. So let's look at this. All right, so we said, assume that they all have the same resistance, the lamps, okay, and the delta V is the same. Okay, in order to determine the brightness of light, I can determine the power. Power is energy per unit time. So if I know the power, so let's start with the series combination. Okay, so for the series combination, let me determine, for example, the current I. So clearly we have two resistances in series. So series combination, first of all. The R equivalent in this case is 2R. Okay, so the current I is going to be equal to delta V divided by R equivalent. So delta V divided by 2R. This is the current. Can I determine the power now through any of the lamps? Yes, because I have the current and I have the resistance, I can use the power is Ri squared. Is Ri squared. So that's R times delta V squared divided by 4R squared. So this will cancel with this R here. So it's delta V squared over 4R. This is how much power one lamp gets. Let's do the parallel combination. Parallel. Okay, so now the resistances are in parallel. I can determine the R equivalent. R equivalent is the product divided by the sum. That's R squared divided by 2R. That's R over 2. So that will be R times R divided by 2R. It's R divided by 2. Okay, now can I determine the power? Yes, because I have the voltage and I have the resistance, so I can determine the power. So this is for the series combination, this is for the parallel combination. It's delta V squared over R. It's delta V squared over R. Which one has more power? Parallel or series? Clearly, this one is more than this one. So the parallel combination gives us brighter light. You can see the power, in fact, is 4 times. The power here is delta V squared over 4R, and here is delta V squared over R. So the power in the parallel combination is 4 times the power that each lamp gets in the series combination. Not only that, we mentioned last time, we should not connect headlights for our car in series. Because if one of them burns, the current will not flow at all, and then the other one will not work. And you know that in your headlights or your car lights, if one burns, the other one is still working. Okay, so not go dark. So it's better to use parallel combination because first of all you get more light, and second, if one of them burns, you still have another one working. Okay, clear? All right, so let me okay, so now I'm going to go to another topic which is very important. These are Kirchhoff's laws, and these are necessary for any electrical engineer to analyze any simple circuit. You need to be able to use Kirchhoff's or Kirchhoff's, I don't know how they spell it or they pronounce it. Kirchhoff, I think he's Russian. So let's assume you have a circuit. So we have 2 EMFs here, epsilon 1 and epsilon 2, and we have 1, 2, 3, 4, 5 resistances. Okay, and we want to analyze the circuit, and let's assume the resistances are given, the EMFs are given, the battery voltages are given, and we want to determine the currents in this circuit. Okay, so first of all, we can see that this circuit has 3 branches. This is one branch, this is the second branch, black one, and the purple one is the third branch. A branch is part of the circuit that has one current. So the current at any point in this branch is the same. The current at any point in this branch is the same, and the current at any point in this branch is the same. So we have 3 branches. Okay. Also, we have 2 junctions in the circuit. A junction is when you have more than 2 branches connected. So here we have 1 branch, 2 branches, and 3 branches. So 3 branches or more connecting at a point. We call that a junction. So we have a junction at point B, and we have a junction at point A. All right, so we have 2 junctions. All right. So First of all, in order to solve for the current, we need to assume a direction of the currents. We don't know if that assumption is correct. It might turn to be correct, it might turn to be wrong. But we have always, so I'm going to assume that the current I1 is going like this, in counterclockwise direction. Current I2 is going from up to down, and current I3 is going to in the also counterclockwise. So this is an assumption, okay? And I'm going to solve for my circuit currents using this assumption, and then we will see how we can, if we made the wrong assumption, how we can correct it. Yes? Every branch? No, it doesn't, not necessarily. For example, well, it doesn't have to be. For example, if we omit this battery, R5 and R1 are still a branch. A branch, by definition, is as part of the circuit, they have the same current. So it doesn't have to have a battery. Yeah. So here, clearly, this current is flowing through this whole branch. Current I2 is flowing through this whole branch, and current I3 is flowing through this blue branch. Okay. So this is the any point in a branch has the same current. Okay. Let's introduce first Kirchhoff's law. It's called the junction rule, or in electrical engineers they call it the Kirchhoff's current law. Okay. It says that due to conservation of charge, the current at any junction has to add to E0, or the sum of the currents entering any junction must be equal to the sum of the currents leaving the junction. It's like water. If you have hoses connected, if we have water flowing in one direction and the other flowing, the water going into the junction has to be equal to the water going out of the junction, because the water has nowhere to go. Same thing, the charge is here. So, for example, here we can write, this is a junction. By definition, or by standard, we take current going in as positive and current going out as negative. So for this branch, I can write I2 is going in, it's positive, I3, and I1 and I2 are going out, so this is minus I1 minus I2 has to be equal to 0. So we take current going into the branch positive and current going out of the branch as negative. So that's why I have negative sign here and negative sign here. I can also write Kirchhoff's current law for this branch. Okay, so let's write it. So we have I1, let's start with I3. I3 is leaving, so it's minus I3. Okay, and I1 is moving in, plus I1. And I2 is moving into the junction, and you can see I2 is moving into it, so this is plus I2 is equal to 0. Notice that these two junctions, the equation, one equation is minus the other equation, is minus 1 times the other equation. So really, if this is equation 1, equation 2 is just minus equation 1. So it really does not add more information. It's the same mathematical equation. All right, so this is the junction rule. The sum of the currents entering any junction must be equal to the sum of the current leaving the junction. This has to do with conservation of charge, and we can write the sum of the currents at any junction in is equal to the sum of the currents going out, or we just say the sum of the currents are equal to 0. Okay, moving in positive, moving out negative. Okay, this is the first Kirchhoff's law. The second law, these are the two necessary laws. Kirchhoff was a German physicist, not Russian. Okay, so the other law says that if we go around a loop, so this is a loop here. This is called the loop rule or the voltage law. The algebraic sum of the changes in potential encountered in a complete traversal of any loop in a circuit must be 0. So that means if we add the potentials, if I start here, okay, and add the potential and go back to the same point, since this point has this point has when you go back to the same point, the sum of the potentials or the sum of energies, you can say, has to be equal to 0. All right, and usually we pick a direction for the loop. So we can pick a clockwise or counterclockwise, doesn't matter. Okay, so this has to do with conservation of energy. And so we write it, the sum of the voltages across or around a loop, this is around the loop, has to be equal to 0. And we will see how we can apply it. So let me apply it here. Okay, so let me start at this point A. So here I'm going through this resistance, and the current, the potential is going to decrease. So I have minus Ri, the potential increases. Then I go through the battery, and when I go through the battery from the negative terminal, the potential increases, plus epsilon is equal to 0, because now I went back to the same point. So you can see epsilon is just equal Ri. We obtain what we are familiar with, which is Ohm's law. Okay, let's see the rules of how we can apply Kirchhoff's laws. There is a sign convention. If your loop direction goes in the same direction as a current through a resistor, we use the potential decreases. The potential decreases from point A to point B. So in this case, this is the loop direction here, the green arrow. In this case, if the loop direction is the same as the current direction and the resistance, the potential decreases. So VA minus VB is minus IR. The opposite, if now the current is that we assumed is in the opposite direction of the loop. So this is again the loop direction that I assumed. Now notice the current is going in the opposite direction. Okay, so in this case VA minus VB is plus RI. So if I go from here to here, the potential increases. So we can write VA minus VB plus RI, or I can just say if the loop direction is opposite to the current direction in the resistance, the potential increases. So these are important, because when we write the equations, we have to pay attention of how we're going. Are we going in the same direction as the current or in the opposite direction as the current? So if we are going in the same direction, we use a negative sign. If we are in the opposite direction, we use a positive sign for the potentials. How about going through a battery? If we go through an EMF, if we go, for example, the loop direction is opposite to the direction of the EMF, in this case the potential decreases, so VA minus VB is minus epsilon. Okay, but if in the loop direction we enter through the negative terminal from point A to point B, the potential increases, so VA minus VB is going to be, in this case, equal to epsilon. So the rule is, okay, this is the rule. If the loop direction enters the negative terminal of a battery, the potential increases. If the loop direction enters the positive terminal of the battery, the potential decreases. So this is what we have to remember. These are 4 sign conventions that we use in order to write Kirchhoff's laws. And if you mix up these, you will get the wrong equation. So you really have to understand these and remember them, so that when you write Kirchhoff's laws, you will write them correctly. Okay? So this is the circuit we started with, and these are the directions of the currents we assumed. So we're going to write Kirchhoff's laws for this circuit. So what I will do, let me take counterclockwise, like the book wants, counterclockwise direction. So I'll take, this is one direction, this is what I will call loop 1, and I will use this as my loop 2. Okay, now doesn't matter. You can pick in one loop one direction and in the other loop the other direction. When you reverse the direction of the loop, the equation will be multiplied by a -1. Okay, so you don't. It's better to be consistent, not to get confused. Use the same direction, for otherwise you might get confused in the signs. So try to avoid using different directions for your loops. Otherwise you get confused. Okay, all right. So let's use this junction. Okay, I'm going to write the equation for this junction. So we have current. Let's start with I1. I1 is leaving, so it's minus I1. I2 is leaving minus I2, and I3 is entering the junction, so it's plus I3 is equal to 0. This is my first equation. Okay, now I'm going to start write the loop equations for loop 1. Okay, let me start at point A and return to point A and go step by step. Okay, so first of all, I'm going through the resistance R1, so we're going in this direction, and we're going in the same direction of the current. And we said if we go in the same direction of the current, the potential decreases. So it's minus R1 I1. Now we're going to go through the battery, but we're entering the positive terminal of the battery. We said if we enter the positive terminal of the battery, the potential will decrease. So minus epsilon 1. Now we're going through R5, and we are going in the same direction as I1. And we said if we go in the same direction, we use a negative sign. So minus R5 times I1. Now we are going to go through, we're going in the same direction, yes. Okay, now we're going to go through this EMF, so we reached this point here, B. Now we're going through the EMF 2, and we're entering the negative terminal. So the plus sigma 2, we said if we enter the negative terminal of the battery, the potential will increase. Okay, now we are going to go through resistor R2. We're going through resistor R2 in opposite direction of the current. So we use a plus R2 I2. This is equal to 0. Now we have went back to point A, and we go through R1, we went through EMF 1, we went through R5, we went through this battery, and we went through this resistor. We went back to the same point, so the sum of the potential equal to 0. So this is my second equation. Okay, let's do for the third equation. The third equation, this is the loop. Okay, it's counterclockwise. So I will start at A. Doesn't matter, I can start at any point, but let me start at A. So first of all, we're going through a resistor R2 in the same direction of the current. So it's minus R2 I2. Now we're going to go through the battery, and we're entering the positive terminal. So do we use a plus or minus? Minus sigma 2 epsilon 2, sorry. Okay, now so we reached this point here. Now we're going to go through R4, and we are going in the same direction as the current I3, so we have to use minus R4 I3. Okay, now we're going to go through the EMF epsilon 3, and we are entering the negative terminal, so the potential will increase, so plus epsilon 3. Now in order to go back to A, we have to go through resistor R3, and we're going through resistor R3 in the same direction of I3. And since we are going in the same direction, we use minus R3 I3 is equal to 0. This is my third equation. Now I have three equations with three unknowns. So I can rearrange these equations. I can write minus I1 minus I2 plus I3 is equal to 0. I can arrange this equation, so I will make them in the same order. So I have minus R1 plus R5 times I1. Okay, and we have a plus R2 I2, and we don't have I3 in this second equation. Let's take the epsilons on the other side. So this is going to be equal to epsilon 1 minus epsilon 2. This is my second equation. صح? Yes. Okay, now let me rewrite the third equation. Same thing, I want to arrange my currents. So I have minus R2 I2, and I have I3 is multiplied by R4 and R3, so minus R3 plus R4 I3, and I will take the epsilons on the other side, so this is going to be equal epsilon 3 minus epsilon 1. So now I have rearranged my terms. So I have I1, I2, I3, I1, I2, I3, and I have taken the constant on the other side. So now I have three equations with three unknowns, and I should be able to solve them. Yeah? You can use the substitution method or the matrix method. Any method will work. Okay, so this is how we solve circuits. We have 3 unknowns. I need 3 equations to solve for 3 unknowns. So I wrote one loop equation, second loop equation, then I wrote one junction equation. So that's 3 equations. If I write this junction equation, adding a 4th equation will not add any value, because this equation here is similar to the equation. It's just multiplied by minus. If I have taken the loop in the opposite direction, clockwise direction, these are the same equation except they will be multiplied by minus 1. So you multiply by minus 1 the first, the second equation, and third equation if I took the opposite. It doesn't matter. The loop direction does not matter, but please be consistent in your loop direction. Yes? The current direction, remember, we assumed these are the current direction. And when we solve, we will find the values of the current. If we find a positive value, that means the assumption we took is correct. But if we find a negative value, that means the assumption we took is wrong. Okay? After we have solved, we can correct the direction of the current. So assume directions for the current. This is important. Assume a direction. It doesn't matter what direction you took. You solve for the currents. And when you solve, you find some positive values and some negative values. The positive values, that means the direction you assumed is correct. For the negative current, that means you assumed a wrong direction. So you can go back and just change the direction of the current. That's it. The magnitude is still correct. You just have to change the direction of the current. All right? So to analyze the circuit, we need to find as many equations as the number of unknowns. So here we have 3 equations with 3 unknowns. Okay? So assume all the resistances and the EMFs are known. We need just to find I1, I2, and I3. So we have, again, 3 independent. We need 3 independent equations, and we already wrote them. Okay, so here, I'm rewriting these equations. We have already done these equations. Okay, so now we can solve. Okay, so we can solve step by step by substitution. For example, you can. So when you are solving circuits, first of all, identify the circuit elements. Identify the polarity of each battery, the EMFs. Assume direction of currents. It doesn't matter if your assumption is right or wrong. You can correct it later. Determine whether the circuit can be reduced, and it can be made simpler. For example, 2 resistors in series, you can combine them, make it 1 resistor. 2 resistors in parallel, there is nothing, you can combine them, make them 1 resistor. So you can simplify your circuit. Be careful. Sometimes when you simplify the circuit, you find it difficult to solve the problem. So I will give you an example later on. When you simplify the circuit, you cannot solve for what is needed. Okay? Anyway, so when you analyze, label all the quantities and use symbols for the unknown quantities. Assign the direction or assume a direction for your current. Okay? You must adhere rigorously to the direction that you assign when you are applying Kirchhoff's rule. So whatever you assumed, use it, the direction of the current. Apply the junction rule to all junctions in the circuit except one. All junctions. For example, here, in the previous circuit, we had 2 junctions. You just need 1 equation. If you have 3 junctions, you need 2 of them, and so on. Okay? Apply the loop rule to as many loops in the circuit as needed. Remember, in the end, you need to obtain the number of equations should be equal to the number of unknowns. By the way, in electrical circuits, we start solving problems with 5 equations, 5 unknowns. We use the calculator, the matrix, and we solve. So when we become very good at it, so we can solve many loops. Okay, you must choose a direction to travel around the loop, clockwise or counterclockwise, and correctly identify change in potential as you cross each element. Be very careful with the signs. This is where most students make mistakes, is they use a minus instead of plus or plus instead of minus. Remember, step by step, and you apply those convention methods. Then you can solve the equation simultaneously. If you're good with calculators, you can plug the constants in your calculator and it will give you. Then you finalize. Check the numerical answer for consistency, and do not be alarmed if you get a negative current. Okay, that means you have guessed the wrong direction. Just change the direction. The magnitude will be still the same. So this is how we solve circuits. Yes. Yeah. So for example, let's see. Okay, so for example, in this circuit, this is a circuit that we just have seen. Okay, we write the equations. This is one junction and two loop equations. And then when we solve by substitution, we find I1 is 0.5 amps, I2 is minus 0.25 amps, and I3 is 0.25 amps. So then you go back to the circuit, and remember, we assumed I2 to be in this direction. I1 we assumed in this direction, and I3 in this direction. So I1 and I3 were correct. So you just go back to the circuit, and you correct the direction. So this is not how the direction of the current flows in this branch, it's this one, I2. But you do it all at the end. The number that you get here, 0.25, is still correct. But the negative sign indicates that the assumption of the direction of the current we took is wrong. So we just go back to the circuit and correct it. So do not make changes while you're solving. You solve with your assumption, and after you find the final results, then you make the corrections. Okay, so let's do this simple problem. So this is a single loop equation. It contains two resistors and two batteries as shown in the figure. Neglect the internal resistance of the battery. Okay, so we don't have. Find the current in the circuit. So we will use a loop equation, and I assumed clockwise direction. Let me start at A, for example. Okay, so first of all, I'm going through the first battery through the negative terminal. So do I use minus or a plus? Plus epsilon 1. Then I'm going through the resistance R1 in the same direction of the current I. Minus R1I. Okay, then I'm going through the battery sigma 2, and I'm going through the positive terminal. So we use plus or minus? Minus. Okay, then I'm going through a resistor R2 in the same direction of the current. Remember, the current is going to be flowing in all the directions here. This is one single loop. Okay, so I'm going in the same direction of the current. Do I use minus or plus? Minus. Minus R2I. Now I want back to the same point, so this is equal to 0. Now I can solve for the current. You can clearly see the current is going to be equal to, so let me take, so this is I times R1 plus R2. Okay, so I'll take it to the right side, and so this is sigma 1 minus sigma 2, and I can get the current is sigma 1 minus sigma 2 divided by epsilon 1 minus epsilon 2 divided by R1 plus R2. So very simple. So this is a single loop equation. So we don't have really to solve. You solve, but you don't need to solve multiple equations. Okay. So when you do that, you find the current. Okay. So now we find the current is minus 0.33 amps, meaning the direction that we assumed is actually wrong. So we say, oh, this is the wrong direction. The current really should be like in this direction. But we do it at the end. Okay, of course, if you are given a circuit and you are given the direction of the currents, use that direction. Use that direction and give the current is minus if it's so. So if you're given a circuit and you're given the direction of the currents, you have to solve with that direction. So if the direction that was given to you is wrong, you will find the negative result. Okay. All right, so this is the same circuit that we did earlier. We wrote the equations for, okay, and so these are the equations we have written for this circuit, and now we have values, so we can replace the R's with the values, and we can replace epsilon 1, epsilon 2, and epsilon 3 with their values, and we obtain this set of 3 equations. So what you can do, for example, I can decide to eliminate one of the currents. So if I want to eliminate I3, okay, I can see that I3 from the junction rule is equal I1 plus I2, okay? So I can replace it in this equation, okay? So you can see the, so 4 minus 4I2 minus 4I1 plus I2. So now I have 2 equations with 2 unknowns, with I1, I2 only, okay? So I rewrite my equations, and I can see from this equation that I2 is equal minus I1 over 2. And I can replace it into this equation to solve for I1. When you solve for I1, you find I1 to be 0.5 amps. Okay. Now I know I2 is minus I1 over I2, so it's minus 0.25 amps. And I3 is equal I1 plus I2. I3 is equal 0.25 amps. So clearly, this is positive, no problem. This is positive, no problem. This here assumption, that means we assumed the wrong direction, and we can correct it in the final circuit. So this is why I crossed I2 and I recorrected it. I showed that this is the right direction of the current. So only after finishing, or after you finish finding all the currents in a circuit, you can correct your guesses about directions. If a current is negative, invert the direction you assumed for it. واضح? So it's not difficult. We can do that easily. Any questions? So if you know how to apply Kirchhoff's law, you are a 50% electrical engineer. Because electrical engineers, they cannot solve an AC or DC circuit without applying Kirchhoff's rules. If you know how to apply them, you can solve for currents, voltages, and so on in any simple circuit. Okay, طبعا these are simple circuits because there are more complex circuits with diodes, transistors, and so on. We're speaking about simple circuits. And we will see later on, even for resistors and capacitors, you can use the same, even for AC currents. Okay, so I will delay the homework until we finish the chapter, so I will delay it, so it's not due tonight. And hopefully tomorrow we will finish and solve some problems from this chapter. So we have only one section left, which is charging and discharging of capacitors. Okay. We still have 2 minutes, okay. So here is another circuit. So let's try to see if we really understand Kirchhoff's law. Find the currents I1, I2, and I3. Okay. So let's assume we want to write it for this junction, and this is for loop 1, and this is for loop 2. Okay. So they already shown us the direction of currents. I1 in this branch, I2 in this branch, and I3 in this branch. So let's write the junction law for this junction. Okay, so let's start with I1. I1 is leaving, so it's minus I1. Okay, I2, where is I2? I2 is also, where is I2? Oh, I2 is leaving, so it's minus I2. Okay, and I3 is entering, so plus I3, this is equal to 0. That's my junction rule. For the loop, let's start with loop 1. Let's start at point B. And we're going through the resistance, so we're going in the same direction as the current, so minus 4I2. Then we're going through the voltage in the positive terminal, so minus 14 volts. Then we're going through the resistance 6 ohms in the opposite direction of the current, so plus 6I1. Okay, and then we're going through the 10-volt battery. Okay, and we're going through the positive terminal, so it's minus 10 volts. And then we have to go through resistance. Oh yeah, we went back to the same point now. So this is equal to 0. That's my loop equation. The second loop, let's start also at point B. We're going through the battery, through the negative terminal. So it's plus 10 volts. Then we go through the resistance 6 ohms in the same direction as the current. So minus 6 times I1. Then we're going through resistor R2 in the same direction of the current, minus R2, which is 2 ohms. Times I3, and we went back to the same point, 0. So we have 3 equations with 3 unknowns I can solve for the currents. We'll see you tomorrow. I will post the grades today. I know you can calculate them from the total. And please, if you have less than 15, please come see me. If you have less than 15, we need really to see what we can do in order to pass the slopes. Okay? I want you to pass the slopes.